Okay, welcome to week 20 of quantum field theory. This is the final QFT lecture. And in some sense, it's the final lecture in our one-year course dubbed Principles of Theoretical Physics. So this is exciting. Today, I'm going to give you guys the basic schematic of string theory, which is sort of very controversial, but nonetheless very important to our sort of understanding and important to how we approach this deep problem of quantum gravity, which I'm sure everyone who is watching this is familiar with. So I thought I would spend a couple minutes sort of giving the background of string theory. What was the motivation? Originally, string theory was developed by Regé and others to address issues in the strong interaction, ironically. No one really conceived of it as a quantum theory of gravity. First of all, let me just say this in case no one knows this. What is the problem? The problem is you have two theories, general relativity, quantum mechanics, quantum field theory, sorry. You have quantum field theory and general relativity, you put them together and you get nonsense, which we've seen many times. Right, and you guys will understand the technical reason. If you quantize gravity in the naive way, which is just the standard way we do things, you get a theory which is not renormalizable, right? You get infinities which you really can't sort of sweep under the rug with regularization or all of the techniques we've learned, right? Adding counterterms, doing the standard stuff. You would need an infinite number of counterterms to renormalize the Lagrangian based on gravity. So that's the problem, and it's still a problem. There are a variety of approaches. There's loop quantum gravity. There's even approaches that are like less studied. Actually, one of the most intriguing ones, in my opinion, is a theory called asymptotically safe gravity, if any of you are interested in looking that up. In fact, that was first proposed by Weinberg, believe it or not. There's also a theory called triangularization, right? There's many schemes that are out there to quantize gravity, but sort of the biggest one is string theory, which is what I'm going to discuss today. And loop quantum gravity would be the second sort of most pervading idea. So string theory was originally proposed to solve several problems in the strong interaction. And it was in the 1980s, and there were two string revolutions. The first string revolution happened in the 1980s on the backs of two men, Michael Green and John Schwartz. John Schwartz at Caltech. Michael Green, I don't know where he is, but John Schwartz, when I went to Caltech, I had a very nice conversation with them about string theory because there was a conference there in Murray-Gell-Mann. He had just recently passed when I went there, so it was very, very nice. Murray-Gell-Mann was a strong supporter of these young string theorists because at the time, string theory was totally archaic. No one wanted to talk about it. And sort of Gell-Mann brought all these string theorists to Caltech. And so in the 1980s, the first string revolution happens where people start to see that if you have some string or 1D filament, that its vibrational modes could possibly give rise to the fundamental particles. And in effect, give you a unified quantum theory of gravity. That was very exciting in the 80s. However, there were many, many problems at that point. The first problem was there were many, many versions of the theory, okay? In fact, there are still many versions of the theory. Okay. And so that problem persisted for 10 years. String theory was again kind of pushed aside because there were many versions of string theory in the 1980s until 1994, the second string revolution. So there were two, they call it. This is when a guy named Ed Witten came on the scene and showed that all of these string theories were really one string theory. So he unified all of them, type 2A, type 2B, you can look them up, there's many varieties, and put them under one moniker called M-theory. This was very, very exciting at the time because it sort of put everything in one framework. Now, string theory fundamentally takes us away from point particles, right? And takes us to 1D filaments. That's the basic idea. And yes, I do sound outdated because I'm taking you about 35 years ago, 40 years ago now, in this description. So just keep that in mind. And it sort of has several benefits and several downfalls. So I'm just going to give you that right now before we dive into some of the mathematics. The first benefit is general relativity is incorporated in the theory from the start. Okay, so general relativity is actually a requirement for string theory. This is very nice. It's not something that comes in later. It's there from the very beginning, which you can now sort of see. Geometry plays a very important role in string theory. Okay. In some sense, string theory was sort of the proponent of something called geometric quantization. That geometry starts to play a very important role in talking about string theory. And that's why the mathematics gets a little bit heavy, because it starts to get very geometric. The second nice benefit is the whole SU3 cross SU2 cross U1 structure of the standard model seems to appear from string theory. However, right now, as of now, no one can recover the standard model entirely from string theory in low energies. Something to consider. Now, there are several sort of issues with string theory. The first is it relies heavily on a symmetry called supersymmetry. In fact, I'm going to show you the bosonic string today, which is just a fancy word for saying I'm going to show you string theory without supersymmetry. But for a variety of technical reasons, it doesn't work. So really, string theory doesn't work without supersymmetry. For those of you that follow sort of pop physics, this is a huge issue with string theory because no one's found supersymmetry yet. The second issue with string theory is it has an unlimited number of vacua, 10 to the 500th possible vacuum states. Okay, that's a problem. Whereas in quantum field theory, you can define the vacuum. You can't do that in string theory. And the final problem with string theory is it requires extra dimensions. Now, I say these are problems. Supersymmetry, these might not be problems, right? If the LHC found supersymmetry, this would not be a problem. This would be a big triumph. However, none of these things have been verified at all. And so in recent years, sort of string theory proper research has kind of died down somewhat. Those of you that are interested, I can get you into the strings conference in a couple of weeks. We can talk about it tomorrow. And you can sort of hear what string theorists are working on now. Okay, great. So let's talk now about some of the mathematics. So in string theory, as you know, there's a characteristic length scale. And what I mean by this is that there's a length scale that is sort of considered the smallest length scale we can probe that's demanded by string theory. In other words, this is the length where people think string theory can be probed. Okay, and this is called the Planck length. So this is just equal to h bar g over c cubed to the 1/2. Okay, this is the Planck length. Oh no, sorry, I think it's to the 3/2. Yeah. And so this is just 1.6 times 10 to the minus 33 centimeters. The issue is to probe the length scale of the Planck length, you need extremely high energies. Okay, energies that we will not really be able to access. It's not really feasible. Similarly, there's a Planck mass. I assume you've heard of the Planck length before, right? I mean, sort of like a common thing people talk about, which is h bar c over g. I think this is to the 1/2, yes. And this is 1.2 times 10 to the 19 GeV over c squared. Okay, so these are sort of the length scales we are operating in. Okay, and sort of here's how the basic structure of relativity and QFT transfer to string theory. So world lines from relativity become world sheets in string theory. So actually, it's interesting because you're describing the string in a two-dimensional space, okay? Where the string sort of, as it moves through space-time, traces out what we call a world sheet with a coordinate in space and a coordinate in time, okay? Feynman diagrams get replaced, okay? So how do we define string perturbation theory? There's no Feynman diagrams. Now what we talk about instead of Feynman diagrams are the interactions between different topologies of world sheets. Okay, so now we describe interactions by different topologies of world sheets. That's a big shift. Okay, and we always assume that our world sheets are smooth, i.e. they have no singularities, okay? So just two more quick, sorry, I'm going off the cuff here, so I just want to make sure I get everything out there. Two more quick things. The idea of extra dimensions, which is sort of like a very popular thing people talk about, came way before string theory. It was thought about a lot, particularly if you're interested in looking at the history. A mathematician named Theodor Kaluza was sort of the first one to think about extra dimensions. And in fact, people thought general relativity would not be consistent in three spatial dimensions. So that was an interesting historical aside. And if you're interested in looking at the precise topological structure of the extra dimensions, they come in a special kind of topological space called a Calabi-Yau space, C-A-L-B-I-Y-A-U, named after the mathematicians who came up with it. Okay, so let's look at the bosonic string. And I'm going to give you all of the sort of machinery. And you could it's not that bad then, just translating everything to supersymmetry. You just have more stuff to keep track of. Okay, because there's extra degrees of freedom now. Okay, so now we describe the string by some function x mu of tau. Okay, this just looks like a world line, but we're going to change this up. So let's just start. I think it's important. Let's just review a relativistic particle. Okay, a 1D relativistic point particle, which we've done before. So the world line is defined by x mu of tau, right? So this is just a relativistic point particle. Eta mu nu, I'm just going to write the signature. So the signature I'll use is minus plus plus plus. That's the signature of the metric. And I hope we all know what this is just then the line element. Okay, that should be review. Okay, what is the action? Does anyone remember the action for relativistic point particle? It's just, so the action is just S equals M ds, right? And in terms of x mu of tau, I can rewrite this action in the following way. So M d tau, right? Because now I'm going to reparameterize this action in terms of the world line. Eta mu nu x dot mu square root. Okay, so hopefully these are things we've sort of seen. And so we demand that the action, first of all, the action is reparameterization invariant. Okay, that's the first thing. Any action is reparameterization invariant. Moreover, we demand that the action is diffeomorphism invariant. What do I mean by that? All I mean is if I have some points on a topological surface I can sort of move all of the points around and the physics stays the same, okay? So if I take a derivative, for example, on the surface at some point, if I then move that point and take the derivative at the new point, I get the same result. Okay, this is what we mean by diffeomorphism invariance. Okay, it's very customary to pick a gauge to work in. So the common gauge to work, so we can pick a gauge to work in because our action is reparameterization invariant. Okay, so this is the common gauge to work in. This is called static gauge. Then I can rewrite my action. Again, if this is all confusing, what I would just do is make a bullet point list, right? And just have them all, and then it's really nice because then you can just go and just kind of look into each one by one and unravel it. Okay, so we work in this gauge called static gauge. I've done this before, so I'm not gonna really. In static gauge, it's easy to work out that the action then becomes this: m1 minus square root 1 minus v squared dt. Okay, where I've just sent t to tau. Okay, and just remember v equals dx dt. Okay, so now we have an action. I haven't introduced a spatial coordinate, right? This is just normal special relativity, right? Point particle moving through. And we did this when we covered special relativity in a lot of detail. So I'm not gonna, where we minimize this action and sort of, right? So if I just drew a schematic, this is tau, x mu of tau, and the world line, well, sorry, this would be xi, spatial, and then this world line is parameterized by x mu of tau, right? So that's what I'm describing right now. And I've written down the action of such a particle. Okay, can I erase the board? Okay. Okay, very good. So now we can kind of do the standard. So let me just rewrite the action in static gauge. So this is just m 1 minus v squared dt. The action is pretty simple. And so now I can sort of do the basic thing. So if I solve Euler Lagrange and minimize this action, I get that dp dt equals 0. That's the equation of motion. Okay, and if you want to solve for the momenta by minimizing the action, you would take delta s, delta v, and this would just be mv over 1 minus v squared, which it is the same relativistic relationship we would want mv gamma. Okay. This is just to show you, I should put an arrow here. This is just to show you that this is the right action for a relativistic point particle. Okay, we've done this before. So if you're interested, look up action, special relativity. I'm sure you'll get tons of stuff that have the same equations in there. Okay, so let's move on to strings now, okay? That was our review of relativistic mechanics. Now we move on to strings. So in string theory, we have objects called branes. Has anyone heard that before? B-R-A-N-E. So brane is some topological surface. And we have something called a p-brane, where p gives you the dimensionality of the brane. Okay, this will make more sense when you hear what I'm saying. So a zero brane is just a point particle. Okay, it's a topological surface with no dimensions, right? It's just a point. Okay, a one brane then is a string. It's a one-dimensional object. Okay, now you can imagine if you have a 5 brane, or you can get all of these weird topological surfaces. We're going to stick with the very basics. So we're going to try and describe a one brane. So now I can, but before we do this, I can now write down an action. So what am I going to do now? So we've covered relativistic point particle. Our goal is to describe what? A two-dimensional kind of version of this, right? That's really what we want to do. Okay, that's the goal. But before I do that, let me write down a general action. Okay, let me write down a general action for any p brane. Okay, that's pretty easy to do now. So how do we do it? So we'll call this SP. So this is just a general action now for any dimensional brane. Okay, and it will go minus TP. And I'm just bear with me. My notation is weird, but d mu p plus 1. And let me define d mu p plus 1. So d mu p plus 1 is minus the determinant square root eta mu mu. Okay, so I'll explain in a second. Del alpha x mu del beta x mu, okay? dp plus 1 sigma. Okay, let me explain. Okay, so this shouldn't be too unfamiliar, right? We have the square root of minus the determinant of the metric. That we've seen many, many times as an action, okay? Especially in GR. And all I've done now is I have the same action now that I've sort of written out in for a point particle, but now parameterized by space-time indices, okay? However, now I have this measure you have to think about, dp plus 1 sigma. Okay, so in the case of a string, this is going to be d2 sigma, right? Because p is 1. Yeah, in the case of a point particle, this is just d sigma. Okay, so sigma somehow now is going to tell me the dimension, is sort of the parameterization I'm going to work in, okay? So just think about that. Yeah. Okay, so just keep this in mind, which we know sigma is one of our coordinates. Okay, can I erase? By the way, just to kind of like put this in perspective, if someone came to me and said, Kyle, you need to give a talk on string theory to experimenters, this is the level I would have it at. So to those that say string theory, that say experimenters don't know any theory, they're completely wrong. This is the level I would put it at, because there's many details I'm skipping, but it's okay. We don't need to be experts right now. Okay, let's continue. Okay, now I have an action. Okay, so now I rewrite x mu of tau as some x mu of sigma alpha. Okay, that's my new world sheet. And this is some p brane. This is the description of some p brane embedded in a d-dimensional spacetime. Okay, so this is a p brane embedded in any sort of spacetime you can imagine. Okay, that's the basic idea. And so if I take the spacetime derivative of this, d alpha x mu, well, how would I write that down? I would just write del x mu del sigma alpha. Okay. You'll see how this works. So let's write down the action now for a string. Okay. Call this x for reasons you'll see in a couple minutes. And all I'm doing now, so I'm taking the general action I wrote. Okay, so integral d mu p plus 1, right? Now I'm going to work it out for a p equals 1 case, and I'm going to take the determinant as well of that action. Okay, so if you just follow that logic, you get something that looks like this. T Oh, by the way, I didn't tell you what T is, TP, right? TP is defined, or T is defined as the tension of the string, okay? So it's some dimensionless quantity that gives you the tension of the string. That's kind of like a weird thing to call it, but just, you know, just kind of agree with it for now and then look into it later. I should have said that. Okay, very good. Okay, so if you kind of work through that whole procedure, there's a lot of algebra, you get the integral of d sigma d tau. So now we see our measure is perfect. It's in terms of sigma and tau, which is what we want, a spatial coordinate and a time coordinate. Okay, versus our point particle only had an integration measure of t or tau. It was just 1D, this is 2D. So all of the metrics, everything I'm writing down is a 2x2 matrix. It's in 2 dimensions now. Okay, that's something very important to think about. Okay, and I'm going to define all of these guys, x dot squared, x prime squared. I'll define all of these guys for you in a second. Minus x dot x prime squared square root. This is what you get. Now, obviously, if I was teaching a proper string theory class, I would take 15 minutes to give you this. So I just want you to know it's fine if you don't see the logic, just look into it later. Okay, and here sigma 0 equals sigma and sigma 1 equals tau. Okay, and remember, because it's only 2-dimensional, so all the indices go from 0 to 1. And I also, furthermore, define x dot mu as dx mu d tau and x prime mu as dx mu d sigma. Okay. So this is the basic string action. Okay. So I encourage you to use the general action d mu p plus 1 action to get this. See if you can derive this. Shouldn't be too hard. It's kind of the same thing. Okay. Now this action is equivalent to the following action, and you're gonna see why. Okay. So this action is equivalent to the following action, S of x and h. So this is just, you'll see why I'm saying x and h. What's very confusing oftentimes when you're first learning this, by the way, oh, I forgot to even show you this. So there are 2 books on the subject I would recommend if you're interested in reading more. This is an awesome book, A First Course in String Theory by Barden-Zweibach. This is really the only undergraduate book out there, okay? That's not to say it's an easy book. It's a very hard book, but if you're an undergraduate and you're sort of good, which you are, you can understand this. So what I'm talking about is in chapter 5 of this book in a lot of detail. So this is covered in like 60 pages. Okay, so just, keep that in mind. And sort of the standard graduate text is String Theory by Joseph Bulchinsky. This is a really difficult book, but it's like, it's the source. Let me know if there's a PDF of this, okay? I'm not sure. If there isn't, I can send you scans if you're interested. Okay, I should have done that at the beginning. When you're introducing a new subject, it's always good to show people sort of good sources. I think Zweibach is the best, honestly. You don't have to go anywhere else. Okay, great. So this action, I'm going to show you how, is identical, or it can be recovered from this action. So this action, S of x and h, goes minus t over 2. And you'll see there's a lot of variables I need to define. So just, when you're writing an equation, bear with me. D2 sigma square root minus h alpha beta. Now alpha and beta go from 0 to 1, right? So there's 2 dimensions. beta mu mu, d alpha, x mu, d beta x mu. Okay, this is a very famous equation. So this is very famous, put a star. This is called the Nambu-Goto action. Named after Yoichiro Nambu, and I forget the other guy, Goto, I don't remember. Nambu was obviously the one who won a Nobel Prize, very famous physicist. And this was the action that they first wrote down. Okay, here H is a metric, okay? And so H is often called the induced metric. So it's called the induced metric. Because it's not a metric that gives you any sort of topology of space-time. It's sort of an auxiliary metric that can sort of be taken out of this action. Now, I'm not going to go into too many of the details, but right. So in the Nambu-Goto action, H alpha beta should really be written as H alpha beta of tau and sigma. And again, H is just the determinant of H alpha beta. Sorry. Okay, so that's the Nambu-Goto. I'm going to rewrite the Nambu-Goto action here. This is Nambu-Goto action. S X H 2 sigma. Okay. Okay, great. Okay, if you solve the Euler-Lagrange equation, you're going to get something. So we're going to call the solution to this T alpha beta. You'll see why. And it goes d alpha x dot d beta x. I would try and solve it and see if you get the same thing. It's kind of complicated. Minus 1/2 h alpha beta. H, do I want to call it gamma? Yeah, gamma delta, del gamma x dotted del delta x. Okay, that's what you get if you solve Euler-Lagrange. And of course, Euler-Lagrange demands that this equals 0. So this is a constraint on all of our equations. And this constraint is that T alpha beta equals 0. Now, something to look up is that this actually mimics, this is why I can't really get into too many details. So you take this, you say, okay, this is just something you solve. Why are you calling this T alpha beta? Because if you look into this, this actually is the same form of the stress energy tensor in 2D conformal field theory. So what we say is that the vanishing of the stress energy tensor, which it does vanish in 2D conformal field theory, is a constraint on all our equations in string theory or in bosonic string theory. So this is a very important condition, even if you don't see how I got there. Okay. Okay, very good. Okay, great. Okay, which leads me into this kind of really nice thing. So in addition to any reparameterization invariance, one very special facet of this action and of a lot of the tools here is that the action is invariant under 2D conformal transformations. That's a very important tidbit, okay? So it's invariant under SL2C transformations. So I can send H alpha beta or this induced metric, okay, to any conformal transformation. We'll call it lambda. So a dilation or any, we'll say dilation of sigma and tau, H alpha beta prime. So that this is a good, so the action has conformal invariance. That's very important. Or while invariance. That's another. While invariance is another word people sort of use to describe this. Okay.
Does that say H prime alpha beta?
Yeah, it should be H. Sorry, I don't know why I put a prime. It should just be H. Okay. So I'm not going to go into the details of how this is the stress. And if you want, you look in a conformal field theory. Or if you just type conformal field theory stress energy tensor vanishes, probably someone on Stack Exchange has gone into detail of how. But I just want to make that comment. Okay. Okay. Okay, so that's a really nice constraint. It gets rid of the induced metric, and it becomes an important sort of constraint on our equations, okay? That this object T alpha beta has to be 0. Okay, so oftentimes we work in a gauge called conformally flat gauge. So in conformally flat gauge, we define, so now we can use the fact that the induced metric is invariant under conformal transformations, okay? And now we can work in a gauge again. This is a technique we use. And so we can write H alpha beta in terms of eta alpha beta times a phase or some dilation. So times e to the phi, we'll just call it phi, where phi is a function of sigma and tau. Okay, so this is just like your most basic conformal transformation. Why is it called conformally flat? Because you're taking the Minkowski metric and multiplying it by some dilation, right? So you're just working in some background flat, right? And so like something to consider is string theory is what we call background dependent. You have to define a background space-time. This is kind of interesting because quantum field theory is background dependent. We're always working in Minkowski space. But if you think about it, general relativity is background independent. Right? General relativity is diffeomorphism invariant. It's background independent. The coordinate choice doesn't matter. Okay? It does matter in QFT and in string theory. Kind of interesting that that's a fundamental difference to think about. Okay, so let me write down the action now in conformally flat gauge. So the action will go again, T over 2. E2 sigma. Beta alpha beta del alpha. X dot del beta x. Just a quick thing. I know I'm writing D2 sigma. This is just convention. D tau is implicitly here always, okay? So like, don't think like, where did the tau go? It's just convention to just write D2 sigma. Okay, now if you solve the Euler-Lagrange equation of this, okay? Yisha's like getting a crash course. Action Euler-Lagrange. Action, you'll learn how to do this when you take mechanics soon, okay? If you just read Taylor, it's not hard. Okay, so if you solve this, you get an equation that goes x double dot mu minus x double prime mu equals 0. Okay, and this is sort of the fundamental starting point for us because this is nothing else but a 2D wave equation, which is really nice. So this is just a 2D wave equation, and so now we have so sort of like what have we been doing so far? We've taken an action. So we have a physical picture, right? We want to describe a 2D world sheet. We want to describe some propagating string with some topology. And so we have an action, and we do what physicists always do, right? We've used gauges. Why can we use gauges to write the action in more convenient forms? Because we have symmetries. Gauges, you can only work in particular gauges by exploiting the symmetries. That's important, right? If I didn't have reparameterization invariance, I couldn't work in static gauge. If I didn't have conformal invariance, I couldn't work in this stage. And so all I've sort of been doing is rewriting things to get an equation of motion, which I can write solutions to. Okay. So now x double dot is just d2 x mu d tau squared, right? And x double prime mu is just d2 x mu d sigma squared, right? Now I have this is just a wave equation. We can write the solution in terms of Fourier components. Okay, so now we can solve this. Okay, let's do it. Okay, but before we do that, let's write down the constraints. So what are the constraints? The constraints are that T alpha beta must equal 0. Okay, and if you write this out, so T alpha beta is symmetric. So T1 0 equals T0 1. And if you just do the quick calculation, you'll find that this means that x dot minus x prime must equal 0. That's the first constraint. And T0 0 equals T1 1. And this, if you compute this just from the formula, okay, so these are our constraints. And so if we put these together, you find the final constraint. So this implies the following sort of main constraint we need to think about. Okay, that's the main constraint. It's always good to write down you want strong constraints, right? That helps you sort of simplify things. Okay, fair warning, some of the formulas I'm going to write down now are going to look really confusing, but don't worry. They're all things you've seen dressed up. That's what I'd like to say when you're first learning string theory. It's like all of the things you've learned are sort of dressed up. But before we do that, so if you're solving a wave equation classically, okay, which like I would do, I would look up wave equation. And then when you see the classical version, you're like, wow, this looks pretty much identical to that, except with an extra derivative on sigma, right? The wave equation is just dependent on time. So, right, we've introduced a new spatial coordinate, sigma. So now we have to define boundary conditions, right? For our wave, or in this case, our 1 plus 1. We can call this a 1 plus 1 object, right? So now I'll start using that terminology. And so we have to write down boundary conditions. So if you remember when I derived the Euler-Lagrange equation many, many months ago for you guys, we talked about two kinds of boundary conditions, Neumann boundary conditions and Dirichlet boundary conditions. So let's just define those again. So Neumann boundary, so first of all, let's do the easy thing. Let's define the boundary conditions if I have a closed string. If I have a closed string, it's really simple, okay? Because the only boundary condition I can have is one that is periodic in sigma, right? So sigma can go to any sigma plus pi, right? It's just closed. So it's just periodic, okay? In sigma. So that's easy. The tricky part is for the open string, because now I have options. Okay, so I will highlight those options now. So what are the options for an open string? Okay, so the options for the open string, I can have Neumann boundary. So Neumann boundary conditions are where dx mu d sigma equals 0. I'll tell you the physical difference between the two. So dx mu d sigma equals 0 at sigma equals 0 or pi. Okay, and Dirichlet boundary conditions are where dx mu d tau equals 0 at sigma equals 0 or pi. So what are the difference between the two boundary conditions? Let's discuss. So first of all, I can integrate this guy. Okay, so the first basic idea, Neumann boundary conditions, I cannot integrate this. However, I can integrate this guy if I'm working in Dirichlet boundary conditions. Therefore, in Neumann boundary conditions, if these are the two sort of boundaries and I have the string propagating, the boundaries are fixed. Okay, whereas in Dirichlet, I can move. So I can have it here, I can have the boundary here, and then I can simply move the boundary around. Okay, so I have more flexibility. So I can move it here, I can move it here, I can do a variety of things. Okay, so that's the main difference. And again, I really should have drawn this out. So like, what are we actually describing here? So let's say this is tau, this is sigma. What I'm describing now is some object that traces a world sheet. But this is defined as x mu of tau and sigma. Okay, that's the basic idea. Because this is a nice drawing to contrast the point particle, right? Okay, that's the fundamental difference. Now you find when you have Neumann boundary conditions that you introduce something called, Dirichlet boundary conditions, that you introduce something called a D-brane, another famous object introduced by Joe Bulchinsky. And so a D-brane is, so of course, if this boundary is moving around, these strings have to live on some object, right? That is also moving around. What are they attached to? They're not attached to nothing. So they're attached to some membrane or D-brane. So you have two objects as well that are moving around. So I'm not going to go into that. Okay, so okay, whatever. We have constraints, we have boundary conditions, we have an equation in motion. Let's solve it. Let's solve it. Let's solve it. So again, we have the equation of motion, x double dot mu minus x double prime mu equals 0. That's what we want to solve, the 2D wave equation. The solution, I can write down the solution for x mu. So I want to write down a solution for x mu of sigma and tau. Okay. And I can write the solution in terms of two parts. We can write the solution in terms of a right moving part and a left moving part, which I'm going to define in a second. So x mu right of tau and sigma plus x mu left of tau. Sorry, this should be tau minus sigma. You'll see for reasons in a second. This should be tau plus sigma. Okay, where again, we have the following conditions. So x mu of, okay, I'm just going to write down the boundary conditions again and the constraints. So the first one is that x mu of sigma plus pi and tau equals x mu of sigma and tau. And the second constraint is that T alpha beta equals 0. Those are the two constraints. And now I can write down the solutions really simply. So now I can write down the solution in terms of XR and XL. These equations are really nasty, so please don't, you write them down and then I'll explain them, okay? Don't get overwhelmed. So X mu R, really these solutions aren't bad. They're just Fourier series solutions. So we've done that many times. For example, in quantum mechanics, right? We've written down Fourier solutions before, so it shouldn't look too unfamiliar. Okay, so it turns out x mu right will be 1/2 x mu plus a parameter I'm going to call ls squared. I will define p mu tau minus sigma. These first two terms aren't as important. What's important is the term that's about to come. Plus I over square root of 2. ls sum n not equal to 0. 1 over n, something I'm going to call alpha n mu. And then the basic e to the minus I. So this is the Fourier coefficient now. Sorry, e to the minus 2i n tau minus sigma. Okay, you're going to see why. Or I'll try and explain what all of this means, but let me just write down x mu l. So again, 1/2 x mu plus ls squared p mu plus sigma. Right, so now it's not tau minus sigma, it's tau plus sigma plus I over root 2 ls. Same stuff. Now I have to write down the Fourier coefficients. This time we'll write this as a tilde. So this is alpha tilde mu n. E to the minus I n. Okay, what does all this mean? First of all, you can see now why they're called right movers and left movers. One is going to take it in one direction, one's going to take it in the other direction. It's just moving the string along the coordinate. Second of all, don't worry too much about these guys. Let's talk about the Fourier coefficients. So they're Fourier solutions defined in terms of some alpha. Okay. Does this term look familiar as a Fourier series solution? I hope so. If not, just look up Fourier series. Should look familiar. We've solved things like this before. Okay, so I have to tell you what alpha are. So first of all, I have an infinite number of modes here, right? Fourier modes, right? Depending on n, the value of n, right? And so I know you guys are going to get angry at me. Yeah, we're going to need to bring up the harmonic oscillator. So what we're going to see is that these alphas behave like raising and lowering operators. Wait a second, is this alpha? Yes, sorry. I had my vaccine 2 days ago, so forgive me. Okay, my second dose. Okay, so these alphas are literally Fourier modes, just like in the harmonic oscillator, right? We had Fourier modes. And they're going to take us through the different excitations of the string. Okay, so it's sort of the same machinery. So let's just define two things. So if I have alpha mu of minus n, so I just want to write down the fact that these Fourier modes are Hermitian. Okay. This will be equal to alpha tilde mu minus n again. So that's just one sort of property of these guys. Or wait, do I need to? Wait, let me think this through. Yeah, no tilde. Yeah, and you can write the same thing for the ones with the tilde. Okay, can I erase the board? Okay. Okay, guys, so now we can quantize the string. We have a solution to the wave equation. We have all the tools that we need. So far, we've been looking at this classically. We have something that is mimicking a raising and lowering operator, right? despite some other technicalities. And so now we can quantize this. What do you think, Isha? Should we quantize this, or should we end this here and kind of quantize? Okay, all right, I can do it. Okay, so what does that mean? First thing, we need some commutation relations. Okay. So we're going to look at the modes of the quantized string. So first of all, P mu of sigma and tau, the four momenta, I'm going to just write this down for you, is equal to delta S delta X dot mu. I just want you to have this formula, which is just Tx dot mu. That's how we define the four momenta in this scenario. And I need that now to write down a commutation relation. So now I can write down a commutation relation between P mu of sigma and tau and X nu of sigma prime and tau. So what is the canonical commutation relation? It's just the same kind of thing, minus I h bar, eta mu nu. Okay. Delta sigma minus sigma prime. Okay, so that's the first commutation relation, which you should be able to show pretty easily. Oh, sorry, you shouldn't be able to show because. Okay, never mind. You're fine. Okay, great. Okay, so now we can sort of write this down in terms of Fourier modes. So first of all, if I just set h bar equal to 1, then this commutation relation, or whatever, you can write it down. You can set h bar equal to 1, who cares? Okay, so in terms of Fourier modes now, I can also write down commutation relations. These are going to mimic the commutation relations of the harmonic oscillator. So if I have some alpha m mu alpha n nu, I can write down a commutation relation m delta m plus n eta mu nu. That's the first commutation relation. Second commutation relation would be alpha tilde mu m alpha tilde nu n. Okay, and this is pretty much the same thing. In fact, it is. Okay. So this is very similar to the harmonic oscillator where we have a dagger equals 1. Okay, why? Well, because this guy is just going to be a 1 or a minus 1, and m is just dependent on the mode. So very similar to the simple harmonic oscillator. And in that sense, alpha mu and alpha tilde mu are raising and lowering operators. So alpha mu is a lowering operator, alpha tilde mu is a raising operator. So this is like A, this is like A dagger. Okay. Taking you through the different excitations. Okay, these would be the modes for a closed string. The quantization of a string that's closed and right moving. Okay. You can easily generalize this to left movers that are closed and so on. And so you get the following equation that just comes from the equation of motion. X prime r squared equals 0. That just comes from the equation of motion. Can I erase the board or? Yeah, okay. Okay, great. So now I can define an object that looks like this. It's going to be a little arcane, but we'll need this to create some algebra. So I'll define something that goes Lm. Okay. So Lm equals, I want that factor out in front, t over 2 integral 0 to pi e to the minus 2 Im sigma x prime r squared d sigma. Okay, and this is not trivial, but I'm not going to show you how to do this. One can write down that you can write this down as a sum of raising and lowering operators, or just dotted to each other. These have a very special name. You're going to see why we need this to make an algebra, basically. These are called Virasoro operators. They're very famous, so if you look them up. Okay. So now the Virasoro operators, okay, so what is this actually doing? Let's just break this down now. Okay. Getting from here to here, whatever. I'm just going to tell you what they do. So the Virasoro operators are going to be the analog of the raising and lowering operators, okay? And that's kind of, you can kind of see that because they're made up of these alphas. So perhaps I was probably wrong in saying that the alphas are not going to act on a state, okay? The Virasoro operators are going to act on the state, okay? So that's just sort of the takeaway. I'm not gonna, it's hard because I'm squeezing like probably 3 weeks of string theory class in an hour. So that, you know, because I just want to show you how it all works and then you can explore it. Okay, so let's define then the string spectrum. Okay, because now I can define all of the excitations of the string based on Virasoro operators, okay? That are going to excite the string or unexcite the string, okay? That's the basic idea. The reason this R comes up is because I'm only doing this in the case of right moving strings, okay? You can easily do this in terms of left movers. Open strings gets a little more complicated because then you have different boundary conditions. And so just do it for closed. Okay, so recall that in quantum mechanics, all my states live in a Hilbert space. So an infinite dimensional vector space where n goes from 0, 1, 2, dot. Okay, and if I want to create a one particle state in quantum mechanics, it's really simple. I have a dagger, right? That's my guy. So I can have any number of a daggers with a normalization root 2 factorial acting on vacuum. Okay, where you have like the normalization that goes 0, 0 equals 1. You have this commutation relation, and you have this between any two arbitrary states. Okay, these are basic things we've looked at before. And so, like, for example, if you have the combination A dagger A on N in quantum mechanics, you just get a one particle state, right? This is quantum mechanics in 5 seconds. or the spectrum of states in 5 seconds. Okay. So now, how do we write the string spectrum? So we'll have a state phi. And instead of working with Hilbert spaces, we're working with Fock spaces. okay, which are just infinite dimensional representations of Hilbert spaces. So now we have a Fock space. And if I have Ln acting on the vacuum, I get 0. And similarly, if I have a Virasoro operator, so that's a Virasoro operator L. And you can define a Virasoro operator such that you get a one particle state. Okay. So this is just the, oh no, this should be on. We'll say 0 on the vacuum. Sorry. Okay. Okay, so now it's useful to write down an algebra. So it's like just sort of the basic way this works. Okay. So the Virasoro operators are just the analog of the raising and lowering operators. Okay. And so if you want to write down an algebra, sorry, let me just check the time. I don't mind running late today because it's the last one, but I don't want to run too late. Okay, we have plenty of time. So if you write down an algebra now between Virasoro operators, you get something that looks like this. So if I have Lm at Ln, which this is a nice exercise to do, you get something that goes m minus n, Lm plus n. Minus c over 12. I'll define this right-hand term in a second. Okay, this is very famous. So if you look this up, you'll get this too. This is called the Virasoro algebra. So this is sort of the first thing you learn in string theory. It's nothing too crazy. It looks crazy, but it's not. You're basically using the tools from quantum mechanics and just redefining things, okay? So this is the algebra between operators. It looks more complicated than the algebra between harmonic oscillator operators, but it's fine. This term, I'll just tell you the name of it, even though it's going to mean nothing to you, is oftentimes called the conformal anomaly term for reasons that are beyond the scope of what I'm showing you, where C is sometimes defined as something called the central charge. You can look that up. Too many details. Okay, great. Okay, so I wrote down the vacuum. So Lm acting on phi gives you, Lm acting on the vacuum gives you 0. But let's write down some excited states. Okay, let's write down some excited states. Okay, because we haven't done that. So how do I want to do that? So first of all, let me write down the mass shell condition. So m squared equals minus p squared. That's the mass shell condition, right? From Q of t. And in the context of string theory, this is basically like saying this guy is equal to 1/2 alpha naught squared, where alpha naught is the first mode. Yeah. Okay, and this is equal to n minus 1. You'll see what I mean by this in 5 seconds. Where n is defined as the following. It's defined as a sum from n equals 1 to infinity, alpha n minus dotted with alpha n. You'll see what I mean by all of this. This is just equal to sum n minus 1 to infinity of n an dagger dot an. Oh my God, am I out of time? I'm definitely going to go over, I think, by about 10 minutes. Okay, so what do I mean by this? If you just look at this, the first excited state, n will equal 1. Okay? So ignore the construction if you want, and just say the first excited state n equals 1, therefore m squared equals 0. Okay? You just think about that for a second. And so I can now write down, so if I have a state phi, let's write down the first excited state. So now this stuff you should understand. I can write this in such a way, if you just work this out, as some zeta mu, which I'll define. Alpha mu minus 1 on phi. Where zeta mu now, no, not on phi. Well, you know what? We'll call this 0 p. Because this is going to create first excitation of the string. Zeta mu is a polarization vector for a spin 1 particle. So it could be any polarization vector that you want. So the string will be polarized, transverse or longitudinally. Okay, so now what's the second excitation? So if I have n equals 2, then m squared equals 1. And the second excited state can be written in the following. So now I can just keep writing excited states. That's what I'm trying to show. This will equal zeta mu, alpha mu minus 1. Okay, so that just is the first piece. Then I'm going to get a second piece plus some lambda mu alpha mu acting on 0 and p. So this is the polarization for some spin 2 particle. Okay. Okay. So let's just break this down really quick. And then I'll show you some string amplitude, the basic of string amplitudes, and we'll be done. Okay, yeah. Good. Okay, so basically what I'm saying here is in order to create excited states of the string, you have to polarize, the string will have some polarization. The first excited state is going to have one polarization. The second excited state is going to have 3 different polarizations or superpositions of polarizations between lambda mu and zeta mu. Okay, so they're just different modes of the string that it can take in some complicated fashion. That's all. Okay. So this guy now, these combinations can give you a variety of different polarizations. Okay, it can give you some polarization in the symmetric part that just looks like the metric. It can give you some combinations of polarizations that look like a scalar. That correspond to a scalar. Or it can give you, so this could be a scalar. Or it could give you polarizations in the antisymmetric part. So this will have a symmetric part and an antisymmetric part depending on the indices or how the indices are structured. And the antisymmetric part, we'll write this as like G minus G mu, will give you some massless. Let me see how I want to describe this. So this corresponds to the metric, this corresponds to a scalar. Does it give you another part? Hold on. No, I think that's it. Yeah. Okay, so if you look into this, you'll see all the different sort of polarization combinations you can get. Okay, so that's sort of the basics of the string spectrum. to sum it up, how much time do I have? Yeah, to sum it up, sum this up really quick. You have raising and lowering operators. They become Virasoro operators. The algebra that tells you how all of this works is the Virasoro algebra. And the string excited states can be made from this Virasoro algebra. Okay, that's the very simple kind of like description. Okay, let's talk about string amplitudes really quick, because this is kind of like what started this whole game. Someone computed some amplitude and it became sort of a cottage industry. So now remember, in normal quantum field theory, the order, so we have a perturbation expansion, right? In what? Lambda, or the coupling, right? The order of the coupling, the order of the expansion is determined by the coupling, right? So you write down your Dyson series expansion, and you have a lambda term, you have a lambda squared term, lambda cubed term, so on and so forth, right? And you draw the Feynman diagrams. So in string theory, the order of the expansion is determined by the topology of the world sheet. It's not determined by a coupling. There's a way to define topologies of world sheets called the Euler number. Okay, you can look into this. That tells you the topology. So if I want to write down the general formula for a scattering amplitude in string theory, I can do it in the following. So actually, I just should say this comment. Historically, string theory was sort of formulated in a path integral way, okay? So this formula, I'm also going to write down in sort of a path integral way. Okay. So D, this formula, a lot of pieces are not going to really, it's okay. I'm just going to give you the general formula, it's fine. DH alpha beta of sigma. Sorry. Dx mu of sigma e to the, hold on, let me rewrite this. E to the minus s of x and h, where s of x and h is just the non-Bogoto action. Okay. I'll describe everything in a second. I'm going to leave a lot of the Feynman rules in sort of a general fashion because there are Feynman rules, but not really for string theory. It's kind of weird. D2 sigma I. Oh, what am I writing here? This should be an alpha. Okay. Okay, so here the V's are some vertex operator, which I'm not going to define for you. Okay. And so this is sort of the basic idea. First of all, this looks like a path integral. Okay, this should be very sort of familiar, where now your configuration space or the measure over which you're integrating is defined over the coordinates for all intents and purposes, because this H alpha beta or the induced metric is always going to drop out based on the exercise we saw. The second term might be more confusing than the first. The first term should be straightforward. So this would be in the free theory. In the free theory, I'd only have the first term, looks like a path integral. The second term, I have some interactions, Okay, don't worry about the structure. But these are some kind of vertex operator between strings. And it's heavily dependent on the topology. Okay, we'll leave it at that for now. There's too many technicalities. Okay, so let me just show you what you get if you solve this guy. So if you have two, and I'm just going to show you sort of the famous result because it's important. So the first result, so first of all, this was written down by someone named Polyakov, okay? If you want to look up this formula historically. And the first amplitude that was calculated was for two open strings. Okay, so people computed the amplitude for two open strings. Okay, and so I'll write down the amplitude in terms of Mandelstam invariance. So S is just, this is just the standard P1 plus, I think it's P3. No, it's P2. P2 squared, and then T is equal to minus P1 minus P4. Okay, so the standard Mandelstam invariance. And if you write down this amplitude, you find that it's equal to the following. So again, this is for two open strings in the ground state. And I'm going to write down some coupling GS squared, even though technically the amplitude is defined by worldsheet topologies and not couplings. It's complicated to get this calculation, but it's good to see what people got. X to the minus alpha of S minus 1. I'll define that in a second. Where, sorry, S is just the Mandelstam invariant. Okay. Minus 1. And I'm sure to Johnson, this will look very familiar. Johnson, do you know how I can solve this guy? This is your favorite integral representation.
Oh,
Oh, come on, Johnson. This is your favorite. How do I solve this amplitude? This should look,
is it similar to the gamma function?
exactly. It's just the Euler beta, the gamma function, the Euler beta function, right? So this is just the integral representation. So if I write down the Euler beta function is defined like this, so it goes the integral from 0 to 1 of x to the x minus 1 times 1 minus x of the x to the x minus 1. And this is just equal to some combination of gamma functions. So gamma of x times gamma of y to the gamma x plus 1. Okay, right, Johnson? Did I get that right? I think so.
Yeah.
Yeah, okay, good. Okay, so this is just the same thing as this. So people figured that out. That was exciting. I think you can write it down. I don't need to write it down, right? In terms of alpha of minus s and so on. And so this amplitude, so then the string amplitude, I'll just write it down just so we're on the same page. Is just equal to GS squared B of minus alpha of S minus alpha of T. Okay, and this was a very famous result. This is called the Veneziano amplitude. So this was the first guy who computed it. Okay. And suffice to say, this was exciting because it started to develop the idea of strings in the context of a lot of sort of the quantum field theory machinery that we use. So this is called, I don't know, I won't write it down, but if you want to look it up, the Veneziano amplitude. And of course, there's a lot of technical detail, but okay. Wait, did I get that right? Is it, wait, Johnson, are both of these powers to the x minus 1? It's gotta be, right?
Let me look into it right now.
Can you just look it up so I don't give them the wrong formula? Okay. I think it's right. I was just using this the other day. In a very annoying way.
It's x minus 1 and y minus 1.
Oh yeah. Okay. But okay, wait. But I should still have a 1 minus x here, right?
Yeah.
Yeah. Okay. Good. Okay. Yeah. Sorry. Okay. Good. Okay. Great. Okay, guys. I've given you a hour and 15-minute tour of what I learned in probably 4 weeks of string theory. So if you have questions, let me know now. And then if anyone has questions before I turn it over to Johnson. Or if it was all clear, that's fine too. Okay. I'm sure it wasn't, but it's fine. You can look things up. Okay, I'll stop recording.